Hey guys, welcome back. Today we're going to be talking about solids. Solids are really quite interesting. It's one of those things that we just kind of take for granted. They're around us all the time. We don't really think about their physical characteristics, but if you think about it in detail, it starts to make sense. What is a solid really? Why are some things harder than others? Why are some things softer than others? Why can we build bridges out of steel, but it's much more difficult to make bridges out of rubber, for example? We're going to talk about all of those things in this lecture. So I hope you enjoy this. Here's some examples of some of the things we're going to be talking about. Here's, of course, a steel truss bridge with steel pilings, or I'm sorry, concrete pilings, and they're actually infused with steel rebar inside to harden the whole thing. And this is actually strong enough to take some of the most powerful floods that this river can develop. Um, Another thing that has to take immense pressures and temperatures is this is a Rolls-Royce jet engine that is installed on I believe, on a Boeing aircraft. These jet engines generate temperatures that are well above anything that we could put in our kitchen, for example, our oven or anything like this. It'd burn a hole right through your standard stovetop oven. So they actually have to make special alloys, titanium, and things like this to be able to make metals that can take those kinds of temperatures. So over the next couple of lectures, we'll be talking about how, in fact, they engineer such a thing. And then, of course, finally down here at the bottom, lower left, this is actually the crystal shape of sugar, also known as glucose in this case. This is not table sugar, which is sucrose. This is the glucose that is actually created by plants and is the kind of the root energy source for human beings and almost the entire animal kingdom and much of the plant kingdom as well. So anyways, like I said, I hope you enjoy this lecture. We're going to have a good time with this. So we just kind of brought up really quickly that there was a crystal structure. We'd mentioned this actually, or was kind of implying this in the last lecture when we were talking about the atomic nature of matter. But let's go ahead and kind of lock this in. So atoms in a solid are arranged in a regular array called a crystal, right? So let's go back to this. Here we can actually see that these crystals are radiating out from some central point. This is called a nucleation point, and they're moving out. And even metals do this. Steel does this. That's actually in here. It doesn't look like this. These are actually, in the case of steel, form cubes. But you get the idea that they form regular arrays. And if you shine an X-ray beam on a solid, and it'll produce a X-ray diffraction pattern. This is evidence of the crystalline nature of the solid. So the reason why is because the atoms themselves, so here's your X-ray tube, it's shooting this stuff through the crystal here and it spreads it around. What happens is these atoms have charges, right? They have, in the nucleus, they have a positive charge. The electrons, of course, have a negative charge. And so you can predict, based upon the shape of the crystal, what's going to happen upon impact with that X-ray. And so the X-ray is going to have these little windows where there's nothing. And then there's going to be areas where you can find them distributed based upon where the electrons and where the protons will allow the X-ray to penetrate through and spread out. So as a consequence of these predictable patterns, we're able to go out and map out entire crystal ranges of all kinds of things. And so there's a whole science called X-ray crystallography. X-ray crystallography is actually what discovered DNA. It's what figured out the original forms of almost all the minerals, including quartz and feldspar and gold and all of these other things. And also was one of the original ways that we started working out the patterns of the atom in the molecular model. So there's a lot of stuff that has come from X-ray refractometry and crystallography. Solids that do not have atoms arranged in a regular array are called amorphous solids. Classic example of that is glass, right? Glass is an amorphous solid. It's not crystalline, and it's in many ways actually is much more of a fluid. It's just a very slow moving fluid. We'll talk about that when we get to fluids, which will be in the next lecture. So this is a little bit of a review. The following kinds of bonds can exist between atoms in a solid: ionic, covalent, and metallic. We covered this in the last lecture, lecture 11. A new one is the van der Waals bonds. This is a very weak bond, and this tends to hold certain crystal groups together loosely. And it's the presence of van der Waals bonds as opposed to ionic and covalent bonds in some minerals that cause those minerals to be pretty soft. Talc talcum powder, which is a mineral. Talc is a mineral anyway. It has a lot of van der Waals bonds on it, and it's the softest, weakest mineral you can put it. We actually put it in baby powder, and we've been using it in baby powder for over 100 years. Anyway, the properties of an atom, or I'm sorry, the properties of a solid are dependent upon the kinds of bonds that exist between the atoms, which is what I'm saying. So here we see this is actually a quartz crystal or series of quartz crystals. And these are all covalent bonds between SiO2 molecules that form this structure here. All right, another property that we kind of need to get out of the way as we're going forward is this idea of density. Density might be familiar to you, but we need to kind of put the definitions out there, so bear with us if you already know it. It's basically the amount of mass per unit volume of a material, so it's mass, which is usually M, usually given in volumes or in units of kilograms, actually. But we usually call it as density equals mass, or M divided by V, or volume. So unit of density is kilograms per meters cubed or grams per centimeters cubed. An example of this, of course, is the density of water is 1,000 kilograms per cubic meter. Okay, so a cubic meter of water is actually the definition of a metric ton. This is the definition of a metric ton right here. All right, or 1 gram per centimeter cubed is another way of kind of reducing it right down to the nitty-gritty. And so here we can see an example of density here. This would be two I guess gases or liquids. They're in cylinders, and you'll notice this one here is a lot less dense than this one here. Okay, there's a lot less mass per the same unit volume, so this is less dense than this one. All right, so there's another way that we can define density as well. It is sometimes expressed as weight density. This is not the preferred way that I do it in my courses, but I need you to know it because a lot of the textbooks have this information in here. And it's simply the weight density is the weight, which is given in newtons, of course, right? Mass times gravity divided by volume. But the way that you can work between these two is pretty straightforward. First off, the unit is Newton meters or cubic meters. But it's really, weight density is the same thing as density. It's just times 9.8 meters per second squared. Or as we sometimes do in this class, we round it to 10 meters per second squared, right? So it's all just kind of going through this acceleration constant of gravity, also known as g. If you subtract the g off, you get density. You multiply it by g, you get the weight density. Here's another example of density. This is a non-uniform density in a system with non-uniform temperature. So down here it's hotter, up here it's colder. We'll get into why this occurs down here, but this of course is a less dense area in the hot region, and this is a cold region up here where it's a lot more dense. And so this would be an example of heat, for example, on asphalt, and the reason why we get low density material down here on the asphalt, or at least in material, I mean atmospheric gases, and then it gets colder as you move up. So density depends upon the mass of the atoms and the spacing between the atoms. This is pretty straightforward, makes complete sense. Uranium, which is the atomic number of 92, it's got an atomic mass of 238. This is a huge monster of an atom. It's a huge, massive atom, and if you held a lump of, just a little lump of uranium in your hand, trust me, your hand would be headed towards the floor. It's a really, really heavy material. And the spacing between the atoms, of course, is a big deal too. Uranium as a solid is a lot more dense than uranium as a gas. Okay, so we just need to keep in mind that density is a property of the material. It does not matter how much material you have. If the density is the same if I'm holding a marble of uranium or if I'm holding a sphere of uranium the size of, maybe a table or something like this, or even bigger. And that's kind of being demonstrated here. This is a real experiment that's been published in Nature, which is a famous science publication. And these are mapping of molecules, and I don't remember which molecules they are, but to demonstrate, they mapped real molecules in predicted different densities, and they in fact have shown that there are in fact different numbers of molecules in the same volume here. So this is real imagery, backscatter imagery is what we would call it, of molecules in a chamber of equal volume to show that the densities are different. Another important property of solids is that they tend to be elastic. That doesn't mean that they're completely compressible, right? But they can be elastic. So what is elasticity? Elasticity is an object that is subjected to external forces may undergo changes in shape and or size. Not all things do. Sometimes you just put a little bit of external force on it, it shatters, it breaks, or it doesn't break, it just takes it. It's very, very strong. So a body's elasticity is a measure of how much it changes when a deforming force, deforming means something that wants to change its shape, is exerted on it and how well it returns to its original shape. Materials that do not return to their original shape are inelastic. So an example of an elastic solid would be this rubber band, for example. And so to understand elasticity, you have to understand something called Hooke's law. Now, we've been kind of hinting at Hooke's law earlier on, and especially in some of the earlier lectures under dealing with Newton's laws. Hooke's law is kind of a modification of Newton's second law. Basically, Hooke's law is another kind of like an F equals ma, but a little different. It's the extension of a spring is directly proportional to the force applied to it. And so that's what we're seeing here. Force is proportional to the change in the displacement on the spring, right? So if you pull on the spring or if you push on the spring, the amount that you pull or push it is proportional to the force, directly proportional in a linear way. And so to put that into equation form, you usually just put a constant right here in the front, and you multiply it by whatever you know the proportionality exists with, and you get an equation. And this is Hooke's law, is F equals K times the change in X. Change in X, again, is just the amount of difference in the motion of the spring. And K is the spring constant. The spring constant is kind of the measure of the stiffness of the spring. We're not going to get into the spring constant and all that much. Just be aware that K is the stiffness and X is the amount of movement. And that's all equals to the force. And we can see this here. There's no or almost no mass on this spring here. That's just simply the weight of the cradle. And it extends so far. You add double the mass, it goes to this. Notice it's a nice linear trend as it goes down. All right, a couple more extremely important physical properties of solids to understand is tension and compression. So when something is pulled on, it is called tension. It's, pulling something apart. When it's squashed, it is called compression. That's when you're pushing things together. And so here we can actually see, here's a girder, which is a steel beam or a metal beam that is usually used in the roofing materials of a lot of big buildings, skyscrapers especially. And imagine if you put a box out here at the end of this girder, what's going to happen? At the top of the girder, you're going to have a zone of tension, but underneath it, it's going to be a zone of compression. And this dashed line here in the middle is a zone where neither one is occurring. Okay, it's a neutral zone, if you will. And so the net result is that this girder is going to bend down. It's going to bend down in this way. Okay, we can go ahead and we can reverse that situation by putting the weight instead of at the end. We can move it right here to the middle. And when, in this case, the tension is going to be on the lower side. It's going to be extending here, and the compression is going to be on the upper side. So you can realize pretty rapidly that if you're building things with girders, you better know where the strength of the girder is, because if you're going to use the former situation, you better know if it's stronger in tension or if it's stronger in compression, because that's going to have a major effect on whether it's going to fail in that situation. Same thing here. Okay, so there's a whole science in the design of girders, it turns out, in engineering. So one of these typical ways that we deal with these things in order to maximize the strength of a girder beam, for example, is to create something called an I-beam. Remember I was telling you there's a whole science to this, so this is an I-beam. It looks like a giant eye. Here's some gentlemen having lunch on an I-beam. This is the construction of the Empire State Building in New York, and you can tell they're having lunch here, and this is a long way down. Anyways, so often construction uses an I-beam, a beam with a cross-section shaped like the letter I. When the beam is used as shown, the shape of the I-beam maximizes strength because the top, which is under tension, and bottom, which is under compression, have the most material. Notice this. So this little section here is not where most of the compression or the neutral stuff is. It's all up here on the top or down here on the bottom. So it maximizes strength because it has the most material at the top and at the bottom, which is under tension and under compression. And it minimizes weight because the middle of the beam that is not under stress has the least material. So remember, this part here has no compression, no tension. It's not actually doing anything. All it's doing is adding weight between these two. So one of the things you do is you remove the sides here, and that might seem a little strange, but if you think about it in detail, all that thing is doing is holding the top to the bottom here, and it's okay to go ahead and make it reasonably narrow. And that actually increases the strength of the beam immensely. Another kind of building method to kind of get around this compression and tension situation are arches. And arches are used all over the place. The Romans have been using arches forever. The Greeks used arches. Some of the great domes that we see are actually a sophisticated form of arch. So anyway, roofs of some older buildings needed many support columns. So you can imagine like the Greek Parthenon would have these beams going across. There'd be Greek columns everywhere holding everything up in every direction. But with the discovery of arches, supporting columns were no longer needed. Why? Because arches take advantage of the capacity of stone to withstand compression. So all of these things are under compression, all of these rocks. This is a Roman aqueduct that was constructed during the time of the Roman Empire. It's been standing here, and there's water still flowing through it, as a matter of fact. This Roman aqueduct has been active for 2,000 years, and it doesn't look like it's going to stop anytime soon. So there's tons of compression in here. Everything is pushing down onto these columns here in the middle, but you have these archways here through which there's a lot of spacing here. They used this ability of stone to increase the strength of the structure. So it turns out this is incredibly strong. In some cases, they didn't even use cement or mortar here in the archways. They could just fit it all together, and it would just hold together through compression alone. Suspension bridges are also arches. So I want you to kind of be aware of what a suspension bridge is, except they are built to withstand tension instead of compression. So instead of pressing everything down to the ground, you can see it's all pulling. Everything is tension, 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 tension. All the compression is right here. There's even tension right here. Right? So all the compression is right at the middle of the beams. The rest of it's all under tension. But look at this. Remember those aqueducts? Here are the arches. This is the exact same design of the aqueducts. You notice I just flipped this image upside down. And you get the same distribution of stresses, of tension and compression, as you did back here. So it turns out that a suspension bridge is just a special form of arch. It's just an upside down arch. And here's of course, the most famous suspension bridge in the world. It's not the longest, but the most famous. It connects Northern California to Southern California. This is, of course, the Golden Gate Bridge. So an arch there's, of course, just like all things, there are all different kinds of categories of arches. They come in all kinds of shapes, and they distribute loads in different ways. So here are two kind of special varieties of arches I want to talk about. So if the arch is supporting its own weight, then the proper shape is what they call a catenary. So the Arch of St. Louis. And so you can see a catenary is demonstrated here. Here's the Arch of St. Louis. And this student, presumably, who's wearing an interesting shirt, has a chain, and he's hanging it down. And he's basically showing that if you were to take this chain and make this point here the length to the top, and let it hang under regular gravity, you could flip it right up in the case of the St. Louis Arch, and it would be able to stand under its own weight. You don't need any supporting columns here in the middle holding it up, and it can actually take some pretty ferocious weather patterns and survive it. And an arch an arch rotated around is a dome. So imagine taking this here and spinning it around and looking at what you get a dome. And of course, this is the Jefferson Monument in Washington, D.C. All right, so one of the interesting things that happens with time when you grow up is you start asking yourself, why is it that a cat can fall out of a tree and survive, but if I fall out of that same tree, I'd get killed? And the reason is this concept called scaling. So you can see, I've got a nice picture here of some kids that are riding around on the size of an ant. Of course, the ant is very large. and it is not necessarily the kids being shrunk down. But even though this is from the set of Honey, I Shrunk the Kids, which is a film from the 80s. Anyway, the interesting thing about this is this ant, it's all scaled up. Despite the fact that it's scaled up, you would think that it would have the same strength or the same relative strength that it does when it's little, but it doesn't. In fact, if an ant was this large, it would hardly be able to walk. It would not be able to walk under its own strength. It's the fact that it's scaled down, it's really, really small, that allows it to lift so many times its body weight that everybody talks about the wonderful achievement of the ant. So anyways, scaling is the study of how the volume and shape, which is to say the size of any object, affect the relationship of its strength, weight, and surface area. So we've been kind of hinting at strength, and we're going to get into weight, but surface area is something we haven't talked about at all, and this is really an important idea. So strength is related to the area of the cross-section, which is two-dimensional and is measured in square centimeters. So the reason why here is the relationship of the strength is you would have to actually imagine slicing this poor ant up and looking at his cross-section, and that area is related to the strength. And the weight relates to volume, which is the three-dimensional and is measured in cubic centimeters. So we know how to do that already. We've been talking about weight density and things like this already. All right, so we'll come to the strength idea here in a moment. Okay, for increases in linear dimension, so in other words, linear meaning as we get this, here we got a block and we're increasing it, we're bringing it to the sides. Okay, the cross-sectional area and strength grow as the square of the increase. So here's the cross-section. So let's double the size of this linearly. So when we do that, we go 2 up and 2 over, and that gives us this block here. And when we do that, it winds up increasing the strength by 4-fold, right? So the strength grows as the square of the increase, okay? The volume and weight grows the cube of the increase. So while the strength only increased 4-fold, the weight increased 8-fold over. So remember that poor ant? I said you got to imagine a cross-section of him. When he was little, he had very little weight, but and relative to his little weight, his cross-section was quite big. But now that he's big, he's got huge weight. He's scaled way up. So he's increased over, the cube of the increase. But the strength of the ant's only gone up by the square. The result is that the poor ant is not going to be able to lift up this huge amount of weight as we now know. And of course, it explains why human beings have a hard time lifting their own body weight in many cases, whereas ants can lift 10 times their body weight. And so on and so forth. You can see this is being demonstrated as we go through here. And you can pause the video and go through this example, but you'll see pretty rapidly, here's a 3x3, which means we have an increase, 9-fold increase, but that would also be a 27 times increase in mass. And then again, a 4x4 is a 16 times increase, but a 64 times increase in mass. So the mass goes up a lot faster than the strength does. So kind of to sum up, we need to finish up with the surface area to volume ratio. And this is important for chemical reactions and how things break down or whatever, but this will be the last slide, and then we'll kind of leave this subject and go on to liquids. So scaling basically says the surface area to volume ratio is the surface area divided by the volume. Pretty straightforward, right? It's a ratio, surface area to volume. And this is proportional to the size squared. So surface area is always something squared, the volume is always something cubed. And if you just do simple algebra on this, you can cross this out, the size goes to a 1, and that leaves a size underneath. So it means that the larger the thing gets, the ratio of the surface area to volume decreases as it gets larger and larger and larger. Let me give you an application of this. You might have 2 people that like to go hiking, for example. One might be large, one might be small. This is actually common amongst couples where you have a male and a female. One is much larger than the other, and they'll go hiking. And what will happen is the larger person in that hiking party will drink water, but will drink less water than the smaller person in the hiking trip. And the reason why is because the larger person is able to retain water within a much larger frame, and they have a smaller surface area relative to that frame in which to radiate the water out through evaporation. Whereas a smaller person has to drink a lot more water because they have a lot smaller volume relative to their surface area. So the water comes in and evaporates basically right out through their skin pretty rapidly. So just kind of how that works. And of course, it has an important effect in how things break down, how weathering occurs in natural environments, and say in geology and geomorphology, how coastlines form. So scaling is a very important deal. All right. So if you have any questions, there's no more examples or math or that we're going to do here. A lot of this is conceptual. But if you have any questions, feel free to send me an email. And until then, have a good one.